All right, hello and welcome to Fiske Planetarium's Dome to Home series. This is our second video, but it is our first in our 6th to 12th grade series. So if you are in 6th to 12th grade, this video is for you. If you are younger, you can stick around with us, but you might want to check out our K through 5th videos. My name is Rémy, and below me we have...
My name is Jeremy. How's it going, everybody?
So we're here live to talk to you about patterns in the solar system. I am a student at CU Boulder and a live presenter at Fiske Planetarium at CU Boulder in Boulder, Colorado.
Yep, and I was a student at CU Boulder. Now I work at Fiske as an outreach presenter and doing navigating.
And Jeremy will be doing the navigating today. So all the navigation that you are going to see right over here is going to be live from Jeremy himself. It might help you to go full screen if you're not full screen so that you can see it a little bit better over there. And as I said, we'll be learning a bit about patterns in the solar system today. But as I go, if you have any questions, feel free to type them in the chat box over there, I believe. And you can also submit questions through a link in the description or comment on the video. While we're doing the video though, chat is what's going to be easiest. Our question master and chat moderator, Amanda, will relay them to me or answer them in the chat. And I'll be sure to pause every now and then for that. So to start though, let's think about what we mean when we are looking for a pattern. So generally what we're looking for is familiarity, predictability, and repetition. Astronomy began as a way of cataloging the repeated motions in the sky so that we could predict what came next. And that's pretty much the process we still use today. We find a pattern, find an explanation, and then inevitably find an exception in either an explanation or we start again. Science is always a process. So in astronomy, to look for patterns, we have to start by going outside, which Jeremy can do right here. So we're outside, it's a nice day. We're looking south right now. The sun is out and we're in this nice field here, but we can't see the whole sky just by looking south. So we're gonna lay down so that we can see the entire sky all at once. So right now, what Jeremy has projected is as if you were laying on the ground. What we have is fair and feel on CU Boulder campus in Colorado, looking at the sky as it is right now, which is about 11 a.m. on April 15th, 2020 for anyone not watching live. And I'm not gonna lie, it's boring and slow to sit here in real time. So let's go ahead and make it move faster. If you could, Jeremy. And we're gonna just start by watching the easiest pattern for us to see in our solar system, day and night. You may have heard of it. So day and night, as you may recall, is caused by the Earth spinning and just where we're facing. So right now, Jeremy has the trail of the sun in the sky. So you can take a look at where it is right there and as it's going. And you may have noticed that in the summer, days are usually much longer than in the winter. So although we have our pattern of day happens and then night happens and then day happens again, the days also have a pattern in their length. And that comes from how high the sun is in the sky. So let's take a look at where the sun traces at different times of the year so that we can see what that pattern looks like and maybe what it might tell us.
All right, let's jump back a couple months. Let's go to January and watch the sun go from rising to setting. All right, so here we are. It is January 15th now. And the sun will be coming up on the eastern horizon.
So you might remember back in January, the nights were pretty short, or the days were pretty short, nights were pretty long. And you can already see what a difference it is between January and where we are now, how high the sun is in the sky, and how long our days are.
Right, and now let's go ahead and jump back. Let's go maybe to October, November. Let's go to September. And we'll do September. We'll do the same process here. So we'll go to a sunrise on September 14th here. and let's watch how the sun moves through the daytime sky. A little bit different now, huh? What do you think, Rémy? How come?
Yeah. How come indeed? So what we're seeing is different times of year, the sun being higher or lower in the sky, which is a really interesting pattern to notice. The reason for this is because the Earth is tilted. So the Earth isn't just straight up and down, it is tilted like this. So there are times of the year where the sun's here, we're tilted like this, and in the northern hemisphere, we're getting really direct sunlight, and the sun is much further overhead than if we were on the other side and we weren't getting very direct sunlight. So you can see here that we have the longest day of the year. Take a guess on which one that is. That would be the June solstice. It's up for a really long time. And then you have the shortest day of the year. That's when it's pointed away. And that would be in December, the winter solstice right there. And then twice a year, day and night are the same exact length. And those are the equinoxes, spring and fall equinox. But let's go ahead and head back to today. And let's see where the sun is compared to those lines.
All right, so here we are again. It's 11:06. And we'll bring up those lines again. So here we have red line marking the highest point in the summer, blue line at the bottom marking the lowest point in the winter.
So you've got the sun there, and it's above the equinox right there. So you can tell that the day is longer than the night. We are not an equal day and night right now. And since we're headed toward that summer solstice, as time goes on, the sun's just going to get higher and higher in the sky, and your days are just going to get longer and longer. But the Earth spinning causes more than just day and night. Let's go ahead and nix the sun here. Who likes the sun anyways?
I love the sun. Provides life for pretty much everything on Earth.
You know what? That's fair enough, Jeremy. I'll take that. So more than just day and night, it also means that stars move in the sky. So as the Earth's moving around, we're seeing the stars a little bit different. The same way that as the Earth moves around, we see the sun in different parts of the sky, or in this case, not at all.
All right, so now as we move into the evening tonight, you'll notice some of the stars start rising. Which direction are stars rising, Rémy?
They're going to rise in the east, and they're going to start setting in the west, same way that the sun does, because that's the way that the Earth turns.
Ah, that's right, that's right.
Yes. So you'll notice here, if, Jeremy, can you put on the star trails so that we can watch how the stars move? Because it looks a little different from the sun because we've got points of light everywhere, not just in one spot. You can see that they're not just going east to west or anything. They are, in fact, doing a circle. And they're all going around one specific point. And you might have already guessed what that point is, but if you haven't, there's a hint. Surprise, it's the North Star up in the north, also known as Polaris. And it is always going to be at that spot in the sky, and all the other stars seem to twist around it as the Earth spins. That's because the Earth's North Pole, or the axis around which the Earth spins, is pointed right there at Polaris. We got really lucky there because the South Pole doesn't have a star right there, so you have a tougher time finding south down there than we do finding north. So great work, Northern Hemisphere. So if you're ever lost at night, because it's in the same spot in the sky, it's pretty easy to find. And it's especially easy because if you find the Big Dipper, which Jeremy has so kindly found, and it's a pretty bright constellation, so you can almost always find it really well. So if you follow that outer edge right there to the next bright star, and you're going to go ahead and find Polaris, the North Star, right there. So now you'll never be lost. You're welcome. So by watching these stars' motions, the sun's motions, we learned a really long time ago about the Earth's spin. And the stars have more pattern to them than just that twirly motion. So have you ever noticed that different constellations are out at different times of the year? And that's actually not true. They're just up at different times of the day. So Jeremy, could you help us out here? Let's say we didn't have an atmosphere. So in a place like the moon that doesn't have an atmosphere, because the atmosphere scatters all the sunlight and it gives us our nice blue sky. But it also means that we can't see anything else because the sky is all lit up with all that scattered light. So if we turn all that off and get rid of that atmosphere and we watch during the day when the sun comes up.
All right, here we are. It's about 4 a.m. right now. I've turned off the atmosphere of Earth. So you should see the sun rising on the eastern, or on the left side of your guys' screens here in a very shortly. Speed up time a little bit more using the power of the virtual planetarium. And here comes the sun. So if we did have an atmosphere, everything would look blue like you normally do if you went outside right now.
You may have seen the sky, yes. But here, now that we don't have our atmosphere involved, now that we don't have all that sunlight being scattered around and causing that blue sky, we can see that the stars really are still out. It's just that the sun is blocking it and we can't see it. So if you're an astronaut on the space station or on the moon, this is what you would see. You would see the sun and all the stars happening at the same time. So which stars we see from Earth during the time of year all depends on where we are in our orbit around the sun. So if our sun's here, we're over here, we're gonna see the stars on the opposite side of the sun. But if we're over here, we're gonna see the other stars. So as we're coming around, just as an example, you're gonna see a pretty recognizable constellation, Orion. You might remember weeks ago, a few months ago, Orion was up during the night, really, really bright. You could see it really, really well. But now that it's up during the day, you don't see it as well. You might see it a little bit after sunset, but it's going away. And in a few weeks, it's going to be really close to the sun and we're not going to see it at all. But then as time goes on, it'll come back around. Just depends on where we are in relation to the sun. So tracking patterns like the sun and stars especially can tell us a lot about where we are in the solar system, in the galaxy, in the universe. And these stars can tell us not only where we are, but also when we are, once we start paying attention to patterns like this. So we also have more than just stars and the sun up in the sky. We also can see planets. So let's take a look.
So we'll zip all the way around again here.
Yeah.
We'll go into nighttime. And I'll turn the atmosphere back on for us. So now we're going back into nighttime. Now it's a few days in the future. Tomorrow night, zip all the way through the night. Currently, from where we're located here in Colorado, we don't have that many planets that are visible in the early nighttime sky other than Venus. What we're going to be doing here is we're going to get up real early in the morning, roughly about 5 a.m. right as the sun is coming up.
Which we're all doing right now, right?
Yes, I get up every morning at 5 a.m. right about here. So it's about 5:20 a.m. and you'll notice a few other objects in the nighttime or in the morning sky besides the stars.
So you've got right there 3 really nice planets to find: Mars, Saturn, and Jupiter. So if you do wake up at 5 a.m., it's really exciting to be able to see all 3 of those so close to each other. And you'll notice a little pattern here. They're all in a line. So maybe 2 of them you could say that's not really a line, Rémy, but once you have 3 of them and you start, mapping where more planets are, and they all end up in that same line. In fact, all the planets are in this sort of line. So if we look up, we take a look at the orbits here there you go. Yeah, thanks, Jeremy. We can see that they all do follow this same line. And this is another one of those patterns that we see. And it is totally different from the stars, though. If we look at those lines and say we were to watch a planet move, which planet should we watch?
Let's do Mars. I like
Okay.
Mars.
Yeah, let's take a look at how Mars moves. And let's compare the way Mars moves to how the stars move around in their circle or the sun just goes across the sky.
All right, so I'm going to transport us here real quick, and we're going to take a look at the motion of Mars throughout time.
So you can see here, Mars does not really move the same way that stars move, or that the sun moves, or that the moon moves. It's just wandering about the sky, and that's actually where the word planet comes from, is the word wanderer in Greek, because they're just going roundabouts everywhere. But if you track them for enough time, you do end up finding patterns there too. So back in the day, astronomers were taking really, really careful notes and measurements of how the planets moved. Like I said, early astronomy was really just writing down what was happening and then figuring out why and working on predicting it. So for a good long while, these sort of patterns told us, okay, well, things are flat around us pretty much. We're all on the same sort of plane. And clearly it all goes around the Earth because we're the center of everything, is what they decided, because that tracks. I mean, everyone thinks they're the center of everything, right? But the model starts getting really complicated. I mean, I do, right? It starts getting really complicated. You can see how Mars right now just did a little loop.
Just for reference, Mars is the red line. The white
Yes.
line is Venus.
Yeah. So Venus also doing loops. So these planets all not only are wandering around, but they're also doing these loops. And astronomers early on were like, cool, I guess the planets are just doing loop-de-loops around us. So it's called retrograde motion when it looks like it's going backwards from what it's usually doing. And it was a really puzzling phenomenon and difficult to work out the explanation. And they decided on something called epicycles, where not only is your planet orbiting around us, but it's also doing these nice little loops. And it just starts getting more and more and more complicated. And when something gets more and more and more complicated like that, you have to start wondering, does this even make sense? Maybe there's a simpler idea here that might make this work better. So even though predictions worked really, really well from all these careful measurements and they knew when these things were going to happen, it was still complicated. And long story short, no, there aren't loop-de-loops. It doesn't really make much sense why that would happen. What it is once you put the sun in the center of your solar system, it makes a lot more sense on why you might get these little loops here, because all the planets are going at a different speed. So the planets closer in move a lot faster than those that are further out. So planets aren't really going backwards at any point. It's just that one is overtaking the other in the orbit. So the one closer might be going faster than that one, and eventually it looks like it's going backwards. The same way that if you're in a car and you're passing another car, it looks like it's going backwards for a moment, but it is still going forward. So the motions look really complex from Earth, but it comes from a really simple model, a lot simpler than everything twirling around in these weird loops. So we can take a look at these kind of weird motions from space and see how much simpler it looks. So Jeremy, if we could blast off.
Alrighty, everybody buckle up.
Buckle up.
Ooh. Flying through the Earth here real quick.
Ooh. What a treat. You can see Orion still up over there.
Here we have
say bye,
the
Earth.
Which orientation should we take a look at of our solar system first, Rémy?
Let's do edge on.
Edge on.
Yes.
You've got it.
Awesome. So as we're going out here, when we can see the solar system as a whole like this, we can look at our simple model, and we can also use all the patterns that we see to solve problems. And the problem that I want to solve today is, how was the solar system made? No one was around when the solar system was made, so we can't just ask around and find someone who was there and they'll tell us all about the good old days, uphill both ways, snow up to my eyeballs. We have to take guesses based on the patterns that we see. So here's one really easy pattern that I talked about before. Everything's in a pretty flat plane here. It looks a little curved because we're looking at it like a dome. Just remember that. But this is pretty flat. All those major planets here are good morning, everyone, are all orbiting in that same plane. So that's one pattern that we like. Let's mark that down. Nice, we got something to work with, but you can't make an entire like theory based on just one pattern. So let's take a look at some more patterns that we can see, get some more clues here. So, oh, awesome, Jeremy, yeah, top down.
All right, so now we've flown in our spaceship above the solar system, looking down at it.
Awesome. So can you make the planets a little bit bigger? And we can take a look at some more patterns. One thing you'll notice as Jeremy's making them bigger is that they're all fairly circular. So that's another neat little pattern we like. We'll log that away.
All right, and now I'm moving time forward extremely, extremely fast so we can see the motion of the planets.
Awesome, yes, thank you. We could sit out here for, a few dozen, hundreds of years and watch them move around, but, fast forwarding time seems a lot easier here. So what you can see is that they're all going the same direction here. They're all orbiting the same direction. There's nothing that's going backwards for some reason. So they're orbiting the same direction, it's fairly circular, and it's flat. So these facts are a huge part of our concept on how solar systems form. There's a lot of evidence on solar system formation on Earth and in asteroids and stuff, but we're going to focus on these motions and patterns here. What this tells us, the way that they're all spinning the same, the way that it's flat and circular, tells us that basically what happened was a huge cloud of gas and dust. The solar system is made of stuff, so clearly it must have started with stuff, began to collapse due to gravity. And as it contracted, it spun around as well. And you can see that they're all spinning the same direction. So that's the direction that that big gas cloud was spinning as it contracted like that. And the smaller and smaller that the cloud gets, the faster it's going to spin. So maybe as it was really, 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 really big, it wasn't spinning very much, but as it got smaller, it starts twirling faster and faster and faster. So it's kind of like, have you watched ice skating before, where you've got an ice skater, they've got their arms out and they're spinning, but not very much. The second they pull them in, they're twirling so fast you can barely see them. That's the same sort of idea there. And as it spins, it flattens out and makes a disc. So you can see our flat disc makes sense using this idea of the spinning. It's the same way that when you make pizza, you've got your big ball of pizza dough and you toss it in the air and they're spinning it around and it starts flattening out. It's the same thing that happens here. And those are some pictures that we have taken of early solar systems way out in the wilds of space that really confirm that this is a pretty decent idea that we have about how this all works. So it continues contracting and collapsing, and the center of this cloud eventually becomes a star. When the core of it is hot enough to start fusing hydrogen. If you want to learn more about stars, definitely come back on May 13th because we're doing a full show on stars and the sun, and we'll talk a lot more about star formation, but we're talking about planets today. So while that core of the big cloud, at about 99% of the mass of the cloud contracting into that star, the outer parts started coming together to form planets. So you've got all these outer parts starting to coalesce together and turn into these really big planets here. And that's our main theory of how it works. And you may have noticed another planet pattern here. So think about all the inner planets. You've got Mercury, Venus, Earth, and Mars. I know planets. And they're all rocky planets, or terrestrial planets is what we call them. And those are all the inner ones are like that. Then if you look at our outer planets, got Jupiter, Saturn, Uranus, Neptune, planets. And they're all like gas and ice giants. They're mostly made of that gas and ice, as opposed to those inner planets that are made of like really rocky stuff. And we believe, and that is because heavier elements, that rocky stuff, not like gases like the hydrogen and helium that's out there, have a much easier time surviving the heat that comes from being that close to the sun. Oh, we've got a question. Where did it go? Do we have comet data? Yeah, Jeremy, can you pull up comets? Yeah, so Calvin wants to know if we have comet data in here. We do. We've got a lot of stuff. So Jeremy, if you want to show us all the comet trails or orbits.
Okay.
Or some comets. Like, do we have Halley's Comet in here?
Let me search around for it.
Yeah. So while he's looking, I'll talk a little bit about comets, because comets are a little different from the way that the planets go around. You might remember comets. While we have the planets going around in this nice circle in this nice plane, comets are coming around at so many different angles. They come from all over the place, and some of their, or most of their orbits are really elliptical, which means they're not circular, they're really oblong. So comets like that maybe don't fit our pattern, but if we like think about the way that the solar system was early on, we have a lot of interactions between these large planets. And so little things like comets that were left over and didn't turn into planets get pushed around by that gravity and end up in really weird orbits like that. So they come from the like Oort Cloud, which is just this huge cloud of more stuff out there around the sun. And it's a lot of just leftovers from when planets were made, because not everything got turned into a planet. We are left with like meteorites, or meteors and asteroids, and the Oort Cloud and the Kuiper Belt, which is a bunch of icy bodies way out there.
Trying to pull up some of those orbits right now. Technical difficulties, please stand by.
Yeah. So there are like thousands of buttons in our system that Jeremy goes through live, just in case you're wondering how this all works on the back end. But while we're looking for that, we were talking about composition. Actually, comets do fit into talking about the composition. Everything further in is that rocky stuff, and further out we have gases and ices, because when you get further away from the sun, there's much less heat. So gases like hydrogen and helium, ammonia come together more easily, make those giant gas planets, and then things are icier out there. It's colder, so you get more ices. So comets are mostly ices that are out there. So the further away you are from the sun, the more gas and the more ice you're going to have.
All right, so I've turned on some comets. They're maybe a little bit hard to see on this display. Let me see if I can blow up the size of them. There we go. Hopefully people can see that. So these are the locations of all these comets right now.
All right, there's also another question. Yeah, so those are a bunch of comets. Canyon Carver would like to know if we can show Pluto's orbit. Yes, we can absolutely show Pluto's orbit as well. So this is fun. Every time I'm at the planetarium and I go, here are our 8 planets, look how nice they look. Inevitably someone yells out, what about Pluto? Save Pluto. So you can see here, Pluto does not fit our pattern of being on that plane. So that's one of the reasons that Pluto was demoted to being a dwarf planet as opposed to one of our major planets. We found a lot of objects like Pluto out in that Kuiper Belt. Like I said, just a bunch of icy bodies way out there past Neptune. So Pluto's the first one we found, of course, and we kept finding more and more of them. Can you pull up some of the other dwarf planets, Jeremy?
Mm-hmm.
Awesome.
There's Ceres, Eris, Haumea, and Makemake, my favorite one.
Yeah, so those are our dwarf planets there. And as we found more and more of them, we started thinking, oof, the more we find, the more planets we're going to have, and the worse this acronym for planets is going to be. So they all sat down and said, okay, well, how are we going to define a planet? And Pluto just didn't quite make the cut. Again, these are like bodies that ended up having like gravitational interactions that flung them out of that usual like plane of the solar system. So there are always exceptions to any pattern that we look at. So when we come up with an explanation, what we want to know is how exceptions to that pattern work. And since this is one of those exceptions, we did have to think about how did the formation actually lead to something like this. And what we figured out is that it was that gravity interactions with the larger planets that led to these weird orbits.
All right. I also just turned on the Oort Cloud, which I think you mentioned earlier, Rémy. It might also be a little bit hard to see, but do you want to maybe explain that a little bit more?
Yeah, so the Oort Cloud, like I said, it's a bunch of leftovers that's way out there around the sun. It's a cloud, basically, is what it looks like here, as you can tell, hence the name. So you have all these comets, those big icy bodies that just have these really elliptical orbits, these really oblong orbits. Instead of being a circle, they're really wide out, which is why comets come in like really irregularly and have really long periods. So you might have a comet that comes once every 100 and whatever years, because that's how long it takes to come all the way around. And it spreads out really far, actually.
Yeah, as you can notice, you can't even see the solar system, at least our usual planets here. And all these little white dots are the Oort Cloud. There you go. And now you can see a little bit more of the ball shape to it.
So there's a question. Let's take a look here. Okay, so one question is Pluto smaller than Earth's moon? The answer is yes, it is in fact smaller than Earth's moon. It's a little baby, bless its heart. We all love Pluto. We also have a question from Zane that says, can you define a planet? I can define a planet. So a planet is something that has enough stuff that it's spherical. So you have, like it's large enough, it's massive enough that it makes a sphere, as opposed to being one of those oblong, rocky asteroids that you see that look kind of like potatoes. So an asteroid's not going to be a planet. So it has to have enough mass to be round. It has to have like enough mass that it's the most like, I'm trying to think of the word, like its gravity is the most important thing in its orbit. So something like Pluto that first off, it's got its moon. So it's almost like having a twin system. And then also having that orbit that's really weird from having been too affected by gravity of those larger planets. It's not dominant in its orbit is the word I was looking for. So you want to, spherical, you want it to have cleared its orbit, and it orbits the sun, of course. All right. So
here I finally found some orbits of the Kuiper Belt objects, which a lot of these are comets that come through. Here you go.
Yes. There we go. So there are more and more Kuiper Belt objects there. And as we find more and more of those Kuiper Belt objects, again, we wondered like how many of those should be qualified as planets, because some of them are fairly large. All right.
Other questions? Other questions?
Are there any other questions?
You can zoom back in.
All right. So let's go ahead and start heading back home. If anything comes to you as we're heading back home, definitely send us in the chat here. Oh, we've got a question, which is, do planets have equatorial bulges, not really spherical? Yes. Okay, so they're not entirely spherical. Nothing's going to end up as a perfect sphere. So remember when I was talking about that pizza dough flattening out, you're going to end up with bulges along there because it flattens a little bit. But there's enough mass that it's not breaking apart or anything. So you want it to be nearly spherical or fairly spherical. And then what about Planet X? Ooh, exciting question. So Planet X is the idea that there's another planet out there that is causing all those weird orbits, like in the Kuiper Belt and those comets, that we just haven't found yet. And that concept has been around for a long time, but we don't have any direct evidence of a Planet X, and we can really make our solar system model fit without a Planet X. So evidence of it is really slim. It most likely doesn't exist. If it does, then cool. You can come back and tell me that I was wrong all along. But it's mostly just an idea, a cool one, but not one that's real. So can we see the sun from other planets? You should come back for our solar system tour. I don't remember which week it is, but we're going to be doing a full tour of the solar system. And we'll be able to see the sun from all of those planets and learn a bit more about all the planets themselves. So that should be really fun. Definitely come back for that. That'll be week 4, whatever that date is, May 6th. May 6th, come back May 6th. Come back every week, actually, to learn more about stuff. All right.
Okay. Anything else? Last questions?
Yeah, final call. Otherwise, we'll go ahead and wrap this up. All right, cool. Let's go ahead and wrap it up. If anything comes to you after the fact, go ahead and submit it either with a comment on the video or preferably through the link in the description. Otherwise, thank you all so much for joining us today for a little live stream. This was really, really fun. Thanks so much. Don't forget to like this video and to subscribe to Fiske to get those reminders of the next video so that you can come for that solar system tour and for learning about stars. And there's even a week on black holes. That'll be really fun. So from all of us here at Fiske Planetarium, thanks so much for watching, and you all have a great week.
Thanks, everybody.